Yeah, so when it comes to the hyperbolic function, it's not a new topic. If we have done, which I believe all of us have done, the trigonometric derivative. So since we have all done the trigonometric derivatives, and also we know some functions of trigonometric, and then what you're gonna do first, we can look at the types of hyperbolic functions that we deal with. So the type of functions that we have. So let me say the type of hyperbolic functions and their derivatives and their derivatives. So first we have cos of hx, which is equal to e to the x plus e to the minus x all over 2. So the one, of course, we're gonna recognize it by seeing the plus in between the exponential function, right? Then the second one we have sine of hx, which is equal to e to the x minus e to the minus x all over 2. And then the third one, we have tan of hx, which is equal to, so tan, you know that this one is sine of hx all over cos of hx, which in this case, if I substitute the sign on top, is minus this all over 2 divided by the cos is e to the x plus e to the minus x all over 2. Now this will be e to the x minus e to the minus x all over 2 times 2 over e to the x plus e to the minus x, which this is the conclusion, e to the x minus e to the minus x all over e to the x plus e to the minus x for the task. Then we come to have a cot. You know what is cot? Cot is 1 over tan of hx, and means that this would be the opposite of this, 1 over e to the x minus e to the minus x all over e to the x plus e to the minus x. Let me make this one big. And this will be e to the x plus e to the minus x all over e to the x minus e to the minus x. And then this will be cos. And we can see we have cos, sine, tan, cos. We have cosec, so or the sec. We have going back with some coming up cosine. Okay. We have cosec hx, which this is 1 over sine hx, which this is equal to 1 over e to the x minus e to the minus x all over 2. This is equal to 2 over e to the x minus e to the minus x. Then we see that this one is for the cosec. Now we have the sec. We have this. We have sec of hx, which is equal to 1 over cos hx, which this is equal to 1 over e to the x plus e to the minus x all over 2, which is this is equal to 2 over e to the x plus e to the minus x. And then now we are done with the functions for the hyperbolic. These are the hyperbolic functions. So we can now look at their derivative. So it's simple to do a derivative of a hyperbolic function, and also it's simple to do a derivative of the inverse of hyperbolic function. So I think these are the hyperbolic functions. We can also look at their inverses first. And then we can look at the derivative. And then when we come to the inverse hyperbolic function, function. So first, we have find I think we started with find the inverse of this. This is ln of x plus root of x squared plus 1. Now, if we check here, whatever value of x that we plug here, this will always be true. This will always exist. So this we can say for all x element of a real number. We come to the second one. We have the cos minus 1x, which this will be equal to ln of, yeah, these guys are having a holiday here, so they just make noise for no reason. X plus the root of x squared minus 1. You see? So check this. X cannot be, if we check inside, x squared minus 1 can only be greater over 0. Is right? And if we make as the formula, we realize that 1 should only be greater over 1. Is right? So we'll forfeit the negative part. So this will okay for this. So we're going to say, we're going to say this. So this will okay for x greater over 1. So we see. Now, if you come to number 3, we can look at, we looked at tan on the hyperbolic functions, or even on the inverse, we can look at the tan. So for tan, this will be 1 over 2 ln of x plus 1 over, so let me write it like this. Let me say 1 plus x over 1 minus x, right? So we say 4 x being between minus 1 and 1. So every time we try to prove this hyperbolic function, we are going to use this interval. So now we look at the other ones. I think we'll also look at cos the inverse function of x. We'll also look at the inverse function of cos x. We'll also look at the inverse function of x. Now, if we look at all these inverse functions, right, it should be simple for us to find the derivative, because already we would have known what is the inverse function of cos, what is the inverse function of tan. So now what we can do, let's look at the derivatives of, we can look at the derivative. So first, if I want to derive sine of hx, we know that sine of hx is e to the x minus e to the minus x all over 2 with the right. And for us to derive this, we're going to derive the numerator, but that remains the same. And we derive this e to the x, we will change to plus e to the minus x all over 2. The question is, how do we do that? So if I derive that, I'm going to keep e to the x. So this is like this. So it's like e to the x over 2 minus e to the minus x over 2. So if I derive this will be, I keep e to the x over 2 times by the derivative of the exponent, minus I keep e to the minus x over 2 times by the derivative of the exponent. This will be e to the x over 2 minus e to the minus x over 2 times minus 1. And this is e to the x plus e to the minus x all over 2 all over 2. And then I keep the base, the denominator, and add the numerator. And then there I'll get e to the x plus e to the minus x over 2. You see, right? And that will be the idea. And this is equal to cos of hx. You see, right? Then now, let's say we want to derive cos of hx. Let's say now I want to derive cos of hx. Let's say I want to derive cos of hx. This will be equal. So I know that cos of hx is e to the x plus e to the minus x all over 2. That's right. And this will be I derive e to the x, I have minus e to the minus x all over 2. This is what? This is sine of hx. So you see that the derivative of cos of hx is not minus sine hx. Is it right? It's plus. It remains positive. So let's keep that in mind here. So now we come on to derive tan of hx. This will be derivative of tan of hx. We know that tan of hx is sine over that, so it's like e to the x minus e to the minus x over e to the x plus e to the minus x, like this, is right? And the tan of x. If I derive this, the symbol must use quotient rule. So I'll keep the denominator on top, e to the x plus e to the minus x, and I derive the numerator e to the x minus plus e to the minus. Then minus, now I keep the numerator and derive the denominator. This will be e to the x minus e to the minus x. And then this will be all over I square the denominator. E to the x plus e to the minus x squared. And then from here, this will be e to the x plus e to the minus x squared minus e to the x minus e to the minus x squared all over e to the x plus e to the minus x squared. So I can divide both sides. I have 1 minus e to the minus x minus x squared all over e to the x plus e to the minus x squared. So remember, this e to the e to the x minus e to the minus x all over e to the x plus e to the minus x is tan x. Is right? So just plug it in. This is 1 minus tan h squared x. And in this case, 1 minus tan h squared x is the same thing as sec of h squared x. So you see, right? What did we learn here? We learned that sec h squared is equal to 1 minus tan of h squared x. Is right? This is what we learned here. So we should know this by heart. So now we know this, and we learned again here that the derivative, we learned again that the derivative of cos of hx is equal to positive sine of hx. You see, right? So this is what we learned there. So keep that in mind. So I think we've done our now uh, cos sine tan. You can do this one, question rule. You can do this one. So in the right in our question group can also do this one. I'll leave that to say try. I'll leave to say try, but but on Saturday night we're going to do that. I'll say try and G CSO called HS over TX or S of HS and then again D over dx or cos x. So let's try this. And after trying this, now we know that we can do that. So now we have tried to find the derivatives of these uh, functions, right? Now we come to the inverse hyperbolic functions. Now I want to find the derivative of these inverse hyperbolic functions. So let's see how we do that. So now I want to find the derivative of cos h inverse of x, which is, and let's start with the one that's fine. Let's start with fine. So here we can use different types of methods, but let me start by sharing the one which we used to do in I think yeah, I think it's yeah, first level. So if you have this, remember you can let y be equal to son of h this, then you multiply both sides by son of h, then you have this here x. Then from here you just apply the derivative of sine hy, which is equal to the derivative of x. And this would be, if you derive this sine, you get cos of hy times the derivative of y with respect to x. This is plus y. So if I divide both sides by cos of that, I get cos of hy. And we know that here cos of h squared y minus sine of h squared y is equals to y from this one. You see, right? So it's simple for us to get this using this method. So from here, we can simply make this cos subject the formula. To make it the cos of hy subject the formula, we take 1 plus sine of h squared y to the other side. Then we root both sides, that one, it goes. The squared this side, it goes. So it means that cos of hy is equal to 1 plus the root of 1 plus sine h squared y. I know you're used to saying that sine squared x plus cos squared x plus 1, but here's a different story. So this is equal to, we know that sine of h, y is equal to x from here. Let's right from here. So this will be 1 over the root of 1 plus x squared. That is the derivative of the inverse sine. So we can also prove that. So we can still prove that in another way. So what did we learn here? We learned that the derivative of sine inverse is equal to 1 over 1 plus x squared. You see, right? And then, or We can use another method, or which is what you learned here. Remember, I gave you these hyperbolic functions. Now, this is the method that you're gonna use. Gave you these hyperbolic functions. Now I say that the inverse sign of the hyperbolic function sign is equals to ln x plus the root of x squared plus 1 for all z. So now it means that I can come and say, or I derive as the derivative of the inverse sign is equals to d over dx of ln of x plus the root of x squared plus 1. These are all positive inside. I can say for all x element of real number. This will be 1 over x. The derivative of ln is 1 over x, 1 over its inside, times the derivative of those inside. You see, right? This will be, I know the derivative of that is 1 plus 1 over 2 root of x squared plus 1 all over, or times the derivative of the inside is 2x all over x plus, I'll show you how I did this one, which this is equal to 1 plus 2x all over 2 root of x squared plus 1 all over x plus the root of x squared plus 1. The 2 cancels out. We have x over the root of x squared plus 1 all over x plus the root of x squared plus 1. And we know that there's something that is not allowed to be both the numerator and denominator. That's it. So we must come and multiply the denominator and numerator by that thing. X squared plus 1, x squared plus 1. So this will be not allowed to be both the numerator and denominator. We can't have such a thing there. Plus x. This one will cancel out. Then on the denominator we have x plus root of x squared plus 1. X squared plus 1. So we know that this will cancel out this. So we have 1 over the root of x squared plus 1. And that tells us that the derivative of the sine inverse of x is equal to 1 over 1 plus, not 1 plus, x squared plus 1. You see, right? So that's what we learned there. So you can use, I prefer this second method because it's what they teach you. So yeah, the other one can say for first level. You're not doing your first level, so can't be using that method. So just right here, recommended. Just in case the other one, you just use it just in case you forget this one by mistake. But I don't believe anyone can forget, right? I don't believe anyone can forget. So now we come to checking the derivative. Let's say try the derivative of cos h inverse x. Now let's find the one of let's find the one of tan. So when we come back, I want to say this. I won't check it on Saturday, but we are still going to do more of this on Saturday. So it means that on Saturday, when we come to hyperbolic, uh, we're just gonna do some touch up on questions, and then we start the uh, partial derivatives. Partial derivatives are simple. After partial, we come to the parametric equation. So we have the tan of this, and we know that the tan of these, we say that the tan is 1 over 2 ln of, then we have 1 plus x over 1 minus x. So we say that this should be in between minus 1 and 1, for x being in between minus 1 and 1. So this will be equals to, well, let me use the other method first, but it's fine, let me use this one. So this will be equals to, we take out the 1 over 2, we derive ln of 1 plus x over 1 minus x. This equals 1 over 2. If I derive ln, I'm going to get 1 minus x over 1 plus x. So that is the inverse of that, right? Times the derivative of the inside, 1 plus x over 1 minus x. So this will be 1 over 2, 1 minus x over 1 plus x. If I derive that, I'm going to keep the denominator. Derive the numerator, get 1, minus I keep the numerator, derive the denominator, get 1, all over I square the denominator. This will be 1 over 2. This will cancel out one of these. So I'm going to have 1 over 1 plus x. On top, I'm going to have 1 minus x minus 1 minus x all over 1 minus x, like that. Then this will be 1 over 2, 1 over 1 plus x minus 2x all over 1 minus x. So the 2 will cancel out. We'll have minus x all over 1 plus x, 1 minus x. So if I factor out a negative on the other one, the denominator will have x plus 1, x minus 1. I factor out a negative on this one. Just highlight it. Factor a negative there, and the negative will come here. The negative will cancel, left with x over x. What did I do here? Okay. Derivative of this, I get, keep this one, and get, keep this, and get 1 minus x. Cancel out that x, and then I get minus 1, keep this, let me see if you, let me check here. I think you're not supposed to give me x at the end. Let me check if the two direct function. Oh yeah, this function is an language. Let's just start with x. It's x minus x plus 1, x minus 1. And then this one should be x minus x plus 1. Let me resume the previous one. Yeah, so here is x minus 1 over x plus 1. But we say that this one can cancel out that one below. So we say that this can cancel out one of these, right? So we're going to have 1 over x plus 1. Then here we'll have x minus 1 minus x minus 1 all over x minus 1. So this will be 1 over x plus 1. We'll have minus 2 over x minus 1. And this will be, this is going to be, the 2 cancel out like 1, x plus 1, and then x minus 1, and then minus. Yeah. So if the 2 cancel out, we're going to have this, right? The 2 will cancel out to this, and then well, when this will cancel out, then when they cancel out, when this cancel out, we're going to be left with minus 1 over x plus z. And then when we check, we're going to have minus 1 over, we're going to have x squared minus 1. If I factor out the negative, I'll have 1 over minus x squared. Then this tells us that the derivative of the inverse of the tan is 1 over 1 minus x squared. You see, right? Then that will be the derivative of that tan. Then it's that simple. Any question? Any question? So if there's no question, then these are the hyperbolic functions. So far, these are the things which I wanted to introduce on this topic. So we'll see when we do more questions on how do we do that. So now let's come to the partial derivatives. If we come to the partial derivatives, we can just let f be a function of two variables. Let's say now we're dealing with two variables, x and y. We know already what we mean when we talk about two variables, right? Which this means that it's coming from chapter 2, not so long. So we have f of x, y. So first, what we have is we have f of x, x, y. So what this means that this is the partial derivative, partial derivative of f with respect to x. You see, we're doing that with respect to x. Sometimes it's denoted by fx, like that. I can just write that. Just is denoted by fx. You can just put it like that. You see, right? So now we come to fy of xy. We say that this is the partial, this is the partial derivative, this is the partial derivative of f with respect to y. You see, sometimes it's denoted by fy. You see that? That is denoted by fy. So when we derive this, we keep y constant. When we derive this, we keep x constant. You see, right? So that's the nice part about this. So we whatever any constant and y, if we are deriving with respect to x, they're going to be considered as a constant. So we won't be using uh, uh, this implicit differentiation. So remember, implicit differentiation says that if I'm deriving xy with respect to x, I have to keep x, derive y, plus I have to keep y, derive x. So this is not the case, right? Here we are saying that if I'm deriving xy with respect to x, meaning that this is fx, right? What I'll get here is y. I'll just come and derive x. Then that's cool. That's it. Is that right? I'll just derive x and that's it. It ends there. So now let's look at some definition. Now we have a definition. We have a definition. A definition says that if we let f, but I've already defined this. Yeah, I've already defined. I've already stated them here. So let's look at this. If we have f of x, xy, using first principle, this is limit as x approaches 0, not x not h, as h approaches 0. Now let me write this first. I think if I write this, also remember this. If I have f of x is equal to the limit, but f prime of x is equal to the limit is h approaching 0, f of x plus h minus f of x all over h. This is the first principle, right? But now if you come to partial derivatives, if we have f of x, xy, in other words, we are saying that we are deriving with respect to x, deriving that function. So when we come to x, we're going to add h, we keep the y as it is, minus f of xy. You see, right? All over h. And if we come to f of y, xy, we're going to say this is the limit as h approaches 0 of f. We keep x as it is because we're deriving with respect to y. You see, keep it as a constant. We add h on y minus f of x, y all over h. You see, right? So these are the two functions that we can come across. So if they say use first principle, you know what to do, right? So these are the partial derivatives. So, or they use a definition of a derivative. So some examples. Now if they say z is equal to f of x, we say right. Then this means that one more want to show the partial derivative, right? This means that the partial derivative of z all over the partial derivative of x, we're deriving z with respect to x. This would mean that we have partial of this f of x, y. This would be f of x, x, y. You see, right? So we're deriving with respect to x. Now, if we say the partial of z with respect to y, this would be the partial y. So having this x, y, this would be equal to f of y, x, y. So I say we're driving with respect to y on this one. So now let's show this. Let's find this. They say find a. We find fx, xy. B. We find fy, xy. C. We find fx minus 1 minus 2. G. We find fy minus 2 minus 3. You see, right? So if we want to find this and we are given a function, so we can easily prove it. So now let's say that the function is, let's say that z is equals to x to the 4 minus 3x to the third y squared plus 7y over x squared minus 2. If I want to find the first one they said I must find what? They said I must find fx xy. And this we know that it's partial x, you see, partial x with respect to this function. So now this will be, if I derive this with respect to x, I'll derive anything that has x. This will be 3 minus, this will be 3, so it won't be 6, it will be 9. It will be 3 minus, if I derive that, I will have put in over 10. That one will become 0, the 2 becomes 0. Remember, if you derive 7y over x squared is the same as 7y x minus 2, you must derive that. You see that if you derive, this will be equals to minus 14y x minus 3. Then I take the minus 3 to the denominator, get that. Instead, I'm just showing the shortcut. Yeah. So that is f of xy with respect to x. Now I want to find f of y, xy. This will be the partial of y, x to the 4 minus 3, x to the third, y to the third, plus 7y over x squared minus 2. So this will be 0, this is 2, minus 6x to the third y, plus 7 over x squared minus 0. This is minus 6 x to the third y. So I'll keep x, this will become a constant, you see, to go because it doesn't have y. So it's going. So this will be this plus 7 over x squared. You see, right? Then the third one, they said we must find fx minus 1 minus 2. So finding fx minus 1 minus 2 is, I know what is the derivative of that, right? It's 4. And then on x, I put minus 1. I'm using this. So it's minus 1 squared. It's 2 squared minus 1, 4. 2. So this will become minus 4 plus 36 plus 28. So we'll get this. Okay, let me check this. That's minus. So this will be minus 4 minus 36 minus 28 is minus 68. So as Fy of minus 2 minus 3. This will be equals to, we know that F of this is minus 6 x to the third. So on x, I'll plug minus 2 minus 3 on 1. This will be equals to minus 6 minus 2 to the third minus 3. So this will be plus 144 plus 7 over 4. And this will be minus 569 over 4. Right, then we get this. So any question here? Do we all understand? Any question? So we all understand, right? So now let's look at this question. So now we have now they say z is equals to cos of 2x plus y all over 5x minus 9y minus ln of x and squared all over x plus y. And you know that this is equals to cos 2x plus y. You can just simplify it to this minus 2 ln x plus ln of x plus y. The reason I'm saying plus, if I say minus here, chance this negative becomes plus. So now we see. Then now they say find this and with respect to y. So the first one to find with respect to x, we know that z is the cos of 2x plus y all over 5x minus 9y minus 2 ln x minus ln of x plus y. So this would be, we derive cos, we get what? We get minus sine over 2x plus y all over 5x minus 9y times the derivative of the inside 2x plus y all over 5x minus 9y. You see, right? So minus 2 over x plus 1 over x plus y. So now we have this. Okay? This one is plus. So we say now that the derivative of that will be x plus 1 over 5x 9y. Now I'll keep the denominator 5x minus 9y and drag the numerator with respect to x and get 2. You see, right? All over, let's spread this Then I'll subtract out. Then I subtract. I keep the numerator plus y, and then I divide the denominator with respect to x. I get that. You see, right? So now this will be minus sine over 2x plus y all over 5x minus 9y. And this will be 10x plus 18y minus 10x plus 5y all over 5x minus 9y squared minus 2 over x plus 1 over x plus y. So now we come and say this will be equals to minus sine over 2x plus y all over 5x minus 9y. Then this will be the 10x will cancel out and we'll have minus 23y over 5x minus 9y squared. Then this will be minus 2 over x plus 1 over x plus y. And then this will cancel out. Instead like the negative, then that will be the solution to this first derivative or with respect to x. So we do have the second partial derivative, meaning that possible to also have the third partial derivative and the fourth and so on. So it just depends on the question that is given. So even this one we could still find the second partial derivative to 110. So let me say try this. Again we found the one of x with respect to x. Now we must try to find the one with respect to y. So let's see what you get. So now let's come to the second partial derivative. Now if we have the second partial derivative, so for the second partial derivative, if we have z being equals to f of xy, here we know before, right? Remember for the first partial derivative, we said that f of x, we said fx is equals to the partial, or I said this, said this z with respect to x. You remember, right? We said that this will be x xy. You remember, right? So which is also like this is partial x of x and y. You see that? But now we come to the second one, the second partial derivative. We say now we can have x, we can have the first partial that we come and apply the second one, denoted by this with respect to x. So this is f of xx, which is equal to, first I start here. You see, right? So the partial of x, I start here going back. Of the inside is the partial of f over the partial of x. So this was this one. You see, right? So that is the pattern there. That outside coming in. So this will be equal to the partial squared f over the partial x squared. And then now I come to f yx. Then f of yx. Remember, I start with the outside. Start with this one, which is the outside. You see, right? And inside I'll have the one which is inside, which is of y. This will be the partial squared f all over the partial of x, the partial of y. We say, right? So this is always the case. There's a rule to this. If you're able to do this, trust me, yeah, yeah, pro. Now we do of y, we have f of xy, which is equal to the partial of y, that's outside, we enter inside, partial of x. Make sure you don't confuse this, y, partial of x. And then we come to f, y, which this will be f of y, which is equal to, now this will be the partial of y, partial x, partial of y is equal to just squared f over partial y squared. Now these are the second partial derivative. So it's simple for us to compute the second partial derivative. So we can just look at some examples. I think we can look at this one example. And we must note that f of xy is equal to f of yx. Always. You say right, that is always the case. So in other words, I'm trying to say that the partial squared of f over the partial x, no, this is the partial one, that outside, partial x is equal to partial squared f, was that outside always the partial x, partial y. So we see this, right? Then we know that this is how the function should be. So now we come to show examples, and then we show how do we find them. Then the first example, they say find the partial derivative. You see, right? We must find all the partial derivatives of. We have f of xy, which is equals to 5x to the 4y minus 7x squared minus 12y to the third. Then now we start with, to find it is, we start with fx. You know this is partial of x, 5x to the 4y minus 7x squared minus 12y to the third. This is 20 x to the third y minus 14x. The 12 goes away, but it's a constant in this case. You see, right? And then now we come to this one. We come to f of y plus the partial of y plus x to the 4y minus 7x squared 12y to the third. This is 5x to the 4 minus 36 y squared. The 7x goes because there's no y there, so it's a constant. And now we find the second derivative. F of x. So this is partial squared, we're dealing with z, right? Z over partial x squared. So this is like this is partial x or the partial this one. You see, right? So I can just write like this. Which this is equals to. So you can just move from here to here. But I wanted to get use of this, right? Then we know that that one, the first partial was what? 20 x to the third y minus 14x. So if I derivate this with respect to x, I'll get 60x squared y minus 40. You say right. And then now solve this with respect to y, and this is squared z all over partial of y, partial of x, the start outside, right? So the partial of y times partial of z, partial of x. This is the same thing as partial of y, f of x. And then this will be partial of y of 20x to the third one minus 40. And then here we'll have 20x to the third. The function will go and become 0. I just derived y only. They say right now I come and find f of y with respect to x. And this is partial squared z over partial x partial y. But outside for in. So this is outside the starting state. And then this will be partial of x, partial of z, or partial y. And after that, this is the same as partial of x, f of y. Etc. And this will be partial of x, and f of x, y is that y equals 5x to the 4 minus 36 y squared. So with respect to x, I'll get 20x to the 10. Etc. Remember, we said from before, we said that this and this are always the same, which is this is how you confirm if you're on the right track. You say right, this and this are always the same. Here's how you confirm if you're on the right track. If you get the same thing, then you're on the right track. But if you're wrong, then you're not on the right track. So let's do the last one, partial of y with respect to y. So we do the partial of y with respect to y. This one, we get a partial squared z over partial y squared. And this is the partial of y, partial of z, 1, equals partial of y with respect to y. And this is 5x to the 4 minus 36 y squared. And this is minus 72y. You say right? And then that. So let me say try to find all the partial derivatives of this. So this is equal to 3x squared e to the x over y. And the second one, try, I can take this, and let's see, f of x y z is equal to x squared is then cos of x squared plus y squared. Yeah, try this. Then this will be the end of our session.